Welcome back. In this video, we will continue with the rest of the material in section 16.6. So surface area of a general parametric surface. So you have a parametric surface which is written in terms of the parameters u and v. So if you look at the domain, this is the parametric domain, which is in terms of u and v, this figure on the left side. So here you have rectangles which are divided by subrectangles. Which are divided by rectangles. The area of this subrectangle Rij is delta u times delta v, which is the length times width, where ui star vj star is a specific point in that Rij rectangle. This parametric domain transforms or gets mapped onto this surface that is shown in this picture. It's a curved one by the mapping R of uv. So this left-hand side one is the parametric domain in u and v. The right-hand side is the surface. So each of this mini rectangle, subrectangle here, gets transformed to the patch. Image of this Rij is a patch Sij. Sij is one patch of the surface. So we are going to find out the area of each of these patches, and then we are going to add them all. We know that we can approximate by a Riemann sum, and the Riemann sum gets translated into a double integral. So that is the idea here. So if you look at this each patch, so it looks like the blue figure here, but you can approximate it by the edges can be approximated by these pink lines over here. So those are the tangent vectors. So you can approximate by RU star delta U one side and RV star delta V on the other side. So we know that we can find out the area of a parallelogram formed in terms of two vectors. So area of the parallelogram will be, we know that it is absolute of the cross product A cross B. The length of the magnitude of the vector A cross B is the area of the parallelogram. The similar idea here, area of this patch of the parallelogram can be approximated by RU cross RV, and of course it is absolute value of that, then delta U, delta V. This you can do for every patch of something like Sij here. You can do this all over the surface, and you can add them all by Riemann sum. That will become an integral. That is the whole point of this basic concept behind this surface area. We are doing the surface area for a parametric surface. So write an expression for the area of a parametric surface. If S is a smooth parametric surface given by R of uv equal to x of uvi plus y of uvj plus z of uvk, where R of uv belongs to D and S is covered just once as uv ranges throughout D, then the surface area of S is given by A of S equal to double integral. What do you expect here? It is magnitude of the vector product, cross product, RU cross RV dA. That is what we stated earlier. Where what is R of U? It is the partial derivative of R with respect to U. What is R is given here in this step. So you are differentiating that R with respect to U. So it is dou x by dou U I plus dou y by dou U j plus dou z by dou u k. When I say dou z over dou u, it means partial derivative of z with respect to u. Same way for R of v, which is dou x by dou vi plus dou y by dou v k j plus dou z by dou v k. So you can do this particular problem number 49, is based off finding the surface area where the surface area is given in parametric form. This is a formula that you need to remember in this part. So this problem number 49 in the additional suggested exercise is based off that formula. Please refer to the video for this section. For this problem number 49. There are other problems also done in that video. For example, problem number 41, problem number 45, and all other problems that I stated earlier. Problem number 19, 35, all these are done as well. Problem number 19, problem number 35. This problem is done in the video section. Problem number 19. So even this problem is done in the video. You may want to refer to get an idea of these problems, because we are stating the formula here, and then you will know how to apply that formula to do these problems by watching the videos. Now, what is the special case to this parametric area, finding the area of the surface in parametric form? What would be the special case? So what we derived earlier was specific to parametric surface written in parametric form. Now what happens when the surface is given in terms of the explicit way, that is z written as a function of xy? When z is isolated in the surface equation, it is called explicit function, explicit way of writing the surface. Explicit representation. For a special case of surface with the equation z equal to f of xy, now what happens is x and y become the parameters. X and y lies in D, and f has continuous partial derivatives. We take x and y as parameters. The parametric equations are x equal to x, y equal to y, and z equal to f of xy. We know that r vector, which is a function of xy now, becomes xi plus yj plus zk. The r sub x, we are going to partially differentiate with respect to x. So it's 1i, then you have 0j because y is considered as constant. Then z is a function of x and y, and you are going to differentiate that partially with respect to x. You can either write that as dou f by dou x or dou z by dou x. Both are okay. When you differentiate partially with respect to y, x is a constant, so 0i plus 1j plus dou f by dou y or dou z by dou y, both are okay. Write like that. To find area of the surface just the way we did, we need the cross product of these two for the integrand. So we write I, J, K as the first row. Second row is 1, 0, dou z by dou x. Third row is 0, 1, dou z by dou y. If you expand this with row wise, I times, so if you do the expansion of this, it's I times, hide the column and the row to which I belongs. So you will have 0 minus dou z by dou x. Then if you do plus j, then you have to hide that column and row, then go from right to left. So that will be negative dou z by dou y, then plus k, and just 1. So what you see here is negative dou z by dou x I minus dou z by dou y j plus k. Thus, you get um, magnitude of the vector Rx cross Ry to be this vector, which is partial derivative of negative partial derivative of z with respect to xi, negative partial derivative of z with respect to yj plus k. So now if you write the area of the surface given by this equation z equal to um, z equal to g of xy, then it becomes a of s equal to double integral over d domain square root of you're going to get the absolute r of x cross ry. So you're going to have, this would be nothing but absolute rx cross ry, or length of rx cross ry dA, where dA is a parametric area. So it is double integral over d rx cross ry. You're finding the length of this particular vector. So it becomes square root of negative dou z by dou x the whole square plus negative dou z by dou y the whole square plus 1 square d8. In other words, double integral over d dou z by dou x the whole square, everything within the radical, plus 2z by dou y the whole square plus 1. And this formula agrees exactly with the formula that we derived in the earlier section in chapter 15. It's exactly the same formula that we derived in chapter 15 for explicit representation of the surface. I'll show this particular example. Find the surface area of a sphere of radius A in the next part of the video, the concept video for section 16.6. Um, area of the surface, area of the sphere, we have done in several ways. Surface area of the sphere, we have done in Calculus 2 class in chapter 8 and chapter 10 and all that. So in this one, we are going to do this in Calculus 3 way, how by means of a parametric representation of a sphere and finding the area. That is what we are going to be seeing. You already know surface area of a sphere is 4 pi radius square. That is a formula that we will be arriving that through the formula that we derived for surface area of a surface um, through parametric representation, which will be shown in the next part of the video, part D of this section. And remember that this section has got a lot of information, and also for the problems that I have mentioned here, you can check the videos for section 16.6. So I'll see you in my next video, part D of this section.